Hi, in this presentation we're going to talk about Newton's second law. So last week we talked about acceleration, and acceleration is just a change in velocity of an object. And the acceleration of an object is directly proportional to the net force acting on it. And so to increase the acceleration of an object, we could increase the net force, or to decrease the acceleration, we could decrease the net force. So we can write it as acceleration and then that little tilde wavy symbol, which means proportional to. Acceleration is proportional to the net force on that object. One of the forces we might deal with when we're talking about acceleration is friction. And friction is a force that depends on a couple of different things. It can depend on what kind of material. And so, say if we have two wooden blocks rubbing together, or we have a wooden block going across a glass top table, or maybe a wooden block going across a carpeted floor. So, the types of materials will affect friction. And supposing we had two wooden blocks, like in this picture over here on the right, and if you run your hand over those blocks, they'd probably feel pretty smooth. But then if you took a magnifying glass or a microscope and looked at those blocks, you would see that there's that surface that felt smooth has lots of irregularities, so little projections and little peaks and valleys um, that create a kind of irregular surface. And that irregularities are what cause friction as the blocks try to move across each other. Another aspect of the materials that might cause friction is the relative stickiness of the atoms. So, say the atoms in one block want to kind of hang on to, say, the electrons in another block. So those atoms don't want to move across each other very easily. They want to kind of stick together. So the kind of material affects friction. And also, how tightly are those two objects pushed together to create friction? So friction can occur with two solid objects in contact, like we saw our two wooden blocks before. Friction can also occur in fluids such as water or air. And if you've ever seen, say, a shooting star, what you've seen is the friction of Earth's atmosphere heating up this little piece of space debris that's entered our atmosphere until it gets hot enough to produce light, and we see it as a shooting star. Friction can also be present in objects at rest as well as objects that are moving. So let's look at our wooden block here that's on our inclined plane. Right now, the incline of the plane is not great enough to overcome the friction of the block. So the block's going to be kind of at rest on that inclined plane. But of course, if we raise that plane and make that steeper, pretty soon the force of gravity pulling on the block is going to be greater than the force of friction between the block and the plane, and the block will start sliding down the plane. So let's look at this in action. We have our friend Joe here. He's pushing a refrigerator across a floor at a constant speed. So if he's moving at a constant speed, there's no acceleration. Now, would you say the force of friction between the floor and the fridge is more than the force of Joe's push, less than the force of Joe's push, or equal and opposite to Joe's push? Well, of course, if we have no acceleration, then the sum of forces acting on the refrigerator have to be zero. So the force of friction is going to be equal and opposite to the force of Joe's push. But let's say as Joe is pushing the fridge across the floor, we see he's accelerating, he's increasing his speed. So what can we say now about the friction between the floor and the fridge? Well, at this point, if the speed of the fridge is accelerating, we have to say that the force of Joe's push is actually greater or more than the friction of the floor on the fridge. Another thing we have to take into account when we're talking about acceleration is how much mass does our object have? And mass is just a measure of the quantity of matter in an object. And it can also be considered a measure of the inertia of an object. Because when we talk about matter, we talk about an object that has mass, that takes up space, and all objects have an inherent amount of inertia. That's a quality of matter, of mass. Now, mass is independent of gravity. So, whether we have, um, say, a 2 kilogram dumbbell here on Earth, or we take it out into space away from Earth's gravity, it's still going to have 2 kilograms of mass. And also, when we look at objects with mass, the more mass, the greater the mass they have, the greater their inertia. And you can kind of think about this. If you have a marble and a bowling ball, of course, the bowling ball has more mass than a marble, and a bowling ball also has more inertia. You have to exert more force to roll the bowling ball than you do the marble, and it also takes more force to stop the bowling ball than it does the marble. And we measure mass using the gram. Now, weight is something slightly different. Weight is the force upon an object due to gravity. So the object has matter and gravity pulls on that matter, and that's what creates what we call weight. And the scientific unit of force that's acting on objects due to gravity is the Newton. And you saw we used the Newton when we did some problems with force last week. We can also use the pound to measure weight. So if you get on a scale, it's probably going to tell you you weigh 100 pounds or 150 pounds or 180 pounds or whatever. Mass and weight are directly proportional to each other. So if an object has more mass, the effect of gravity on it's going to be greater, so it's going to have more weight. Now, it's really hard sometimes for us to keep mass and weight separate, and it's especially easy to get them confused. But it's important to remember that mass is more fundamental than weight. Mass is completely independent of gravity. Mass is is a property of the matter that's making up the object, just like inertia. Okay? So let's say we took an anvil and we weighed it here on Earth, okay, and say we put it on a scale and it weighs 220 pounds. If we put that anvil in a spaceship and took it to the moon, now the moon's gravity is only a fraction of Earth's gravity. So if we put that anvil on a scale on the moon, it's going to weigh much less than the 220 pounds it weighs here on Earth. But did its mass change? No. The amount of matter in the anvil is still the same. So if the amount of matter is the same, its mass is the same, its inertia is the same, whether it's here on Earth, on the moon, or out in outer space. So when we're measuring mass, we can say that 1 kilogram, if it's subjected to Earth's gravity, has a force equivalent to about 10 newtons. It's actually 9.8 newtons if we want to be very precise, but just like when we were talking about acceleration, we're going to round that up to 10 to make our equations easier to, to calculate. There's also a relationship between kilograms and pounds. So a kilogram exerts about 10 newtons at Earth's surface, and that's about the same amount of newtons that 2.2 pounds has at Earth's surface. So we can say 1 kilogram is equal to about 2.2 pounds at Earth's surface, or 10 newtons. And then we can also say that that means 1 pound is about equal to 4.45 newtons. Okay. And when we think about this force in newtons and the force of gravity and mass, we can actually say that to have weight, we have to have mass being multiplied by some form of gravity. So weight is usually abbreviated in physics as mg, mass times the force of gravity. So let's look at our anvil again. Say our anvil has 100 kilograms of mass. So how much would that weigh on Earth? Well, that would weigh, if we put it on a scale, 220 pounds. Now, do you think of with this anvil with its 100 kilograms of inertia, would it be easy to pick up and shake here on Earth? Not for most people. I mean, if you're in one of those strongman competitions, maybe, but for most people, no. That would not be easy for us to move that anvil to shake it back and forth. Now, if an astronaut takes our anvil into space away from Earth's gravity, is it going to be easier for him to shake that anvil? No, because while the anvil doesn't weigh anything in space, its mass, or its measure of inertia, is still going to be 100 kilograms. So it's going to be just as hard for that astronaut in space to pick up and shake that anvil back and forth or to move that anvil as would be for him right here on Earth to move that anvil. There's a link to a video on our Moodle site that's called the inertia ball experiment, and I'm going to ask you to pause this presentation in just a second and go watch that video. And I want you, when you watch the video, to predict if we have a ball hanging from a string attached to a hook, and then there's another string underneath the ball, what's going to happen if I pull that string very quickly? And then what do you think is going to happen if I pull that string very slowly? So let's pause here and you go watch that video and then come back to the presentation after you've watched it. Okay, so as you saw in the video, if we pull that string very quickly, the inertia of the ball prevents any of that force from being transferred to the upper string, so all the force is taken by the lower string and the lower string breaks. But if we pull the string very slowly, now our force, in addition to the weight of the ball, is all transferred to the upper string and the upper string breaks. So looking at acceleration and its relationship to mass, the acceleration of an object is going to be inversely proportional to its mass. So we can write that formula as this little equation: acceleration is proportional, the little tilde guy again, to 1 over the amount of mass. Okay, so if we have a mass, say we'll call that mass 1, so its acceleration is going to be proportional to 1 over 1, which is 1. But if we double that mass, now its acceleration is going to be 1 divided by 2, and so that's going to be 1/2 the acceleration of the one mass. If we triple that mass, now we have 1 over 3. We're only going to have 1/3 of the acceleration. But let's say we go the other way. What if we half the mass? So instead of 1 over 1, we have 1 over 0.5. And now, since we've half the mass, our acceleration is going to be twice of what it was originally. So acceleration is inversely proportional to mass. The more mass, the less acceleration. Reduce the mass, more acceleration. And that brings us to Newton's second law of motion, which says the acceleration produced by a net force on an object is directly proportional to the net force in the same direction as the net force and inversely proportional to the mass of the object. So the more force we put on an object, the more acceleration. And as we saw last week when we were doing some problems with our vectors and our net forces going in different directions, the acceleration is going to be in the same direction as our net force, and then it's going to be inversely proportional to the mass of the object. So the heavier or more mass our elephant has here, the less acceleration we're going to get when we try to push him. So we can write Newton's second law in equation form. Makes it a little easier to deal with. So we can say that force equals mass times acceleration. And we write that as F equals ma. And if we're doing equations and we have different variables to punch in, we can rewrite it to make it a little easier to do the math. So we can write that as acceleration is going to be our force divided by our mass. Or we can say our mass is our force divided by our acceleration. And basically all this tells us is that if we increase the net force, double the net force, our acceleration is going to double. And then if we double the mass, our acceleration is going to be half. Let's look at this in action. So let's say we have some bricks and we're going to accelerate them in the top pictures by the force of one hand, and we'll just call that one hand of force. And so we get a certain acceleration when we accelerate one brick, one hand's worth of force. Over here on the left in the second picture down, we see if we have two hands of force, say someone else is helping us push the bricks, we're going to get twice as much force pushing that brick and twice as much acceleration. Okay. Over here on the right in the second picture, if we have the same force, one hand of force, but we add a second brick, okay, now we're only going to accelerate half as much because we have the same force, but twice the mass. At the bottom down here, now we have again two hands of force, but we're doubling the mass. So now we have two hands of force on two mass, and we basically have the same acceleration as we do in the top left picture with one hand of force on one brick. And then in our final picture over here on the bottom right, if we have three bricks but still only have one hand of force, we're only going to have 1/3 as much acceleration as we had in the top pictures. So let's look at, thinking about the picture we just discussed earlier, let's look at this. So when objects are in free fall, as we discussed last week, the only force acting on that object is gravity. There's no friction, no air resistance. And we call that acceleration due to gravity as g. And as we discussed last week, we have that number as 10 meters per second squared. So the greater the mass of the object, the greater the gravitational force acting on it. So knowing that, here we have one mass, a brick of one mass, and then we have a brick of two masses. Which one do you think will fall faster? Well, if you just think about the force of gravity acting on the mass, you might have said, well, the two mass brick's going to fall faster. But that's not quite true, because the greater the mass of the object, sure, the greater the force of gravity pulling it towards the earth, but it also has more inertia. And so it's going to resist that tendency to move. Okay? So the acceleration of both bricks is the same. Okay? Twice the force on twice the mass gives the same acceleration. Okay? So, for instance, let's look at our one mass brick. So, the force of gravity divided by the mass of that brick is going to equal our acceleration g. But if we double the force pulling on the brick and double the mass, well, 2 times divided by 2 is still 1. We're still going to have g, our acceleration, 10 meters per second squared. So the greater the mass, sure, the greater attraction by gravity, but also the greater the inertia. So let's say we have a 5 kilogram iron ball and a 10 kilogram iron ball, and we drop them from rest, and they're in free fall. There's no air resistance. Would you say the acceleration of the heavier ball will be less, the same, or more? And of course, as we just saw, the 10 kilogram ball has more mass, but it also has more inertia. It's going to resist motion more. So in free fall, the 5 kilogram iron ball and the 10 kilogram iron ball are going to have the same acceleration. So far we've been talking about free fall, which is where objects are falling only under the influence of gravity. There's no air resistance, no friction, just gravity. But that's not always how the case is going to come to be. Sometimes we have objects that are falling through air, so they are going to encounter friction or air resistance. So in non-free fall, the object is falling downward through the air. The force of gravity is pulling it downwards, just like our objects in free fall. But now we have the air is resisting it. The drag of air on the object is exerting a force pushing up on the object. So this object in non-free fall is not going to have the acceleration that our free fall objects are. It's going to be less. So our acceleration is going to be less than that 10 meters per second squared. So to have non-free fall, we have to have air resistance. And it depends on two things, how much air resistance we're going to have. It depends on the speed of the falling object and how much frontal surface area that object has. So objects that have a larger surface area are going to encounter more air resistance, and objects that have less surface area are going to encounter less air resistance. So think about if you jump out of a plane, you're going to be falling pretty fast, and there's going to be not that much air resistance against your body. But if you pull the cord and your parachute opens up, now there's a huge surface area that's encountering air resistance. So there's going to be a lot more air resistance because your parachute has more surface area. So when we have objects in non-free fall that are moving fast enough to build up that air resistance starts increasing as they fall faster and faster. And pretty soon, that air resistance can build up enough to equal the force of gravity pulling that object down. And when that happens, the force of gravity pulling it down and the air resistance cancel each other out. So we have no net force. The sum of the forces are going to equal zero. And of course, as we learned last week, when there's no net force, there's no acceleration. The velocity of the object is not going to change anymore. And it's important to realize this doesn't mean the object stops. It's still going to be falling, but it's not going to be accelerating anymore. It's not going to be falling any faster. And when the air resistance equals the force of gravity on an object and the net force becomes zero, we can call that terminal speed. And this is when acceleration stops. We can also call this terminal velocity, which is the same as terminal speed, but we're just implying a direction. Terminal velocity is also a really cheesy 90s movie. If you want to check it out, it's very entertaining and very dumb. So let's put this in action. Let's say we have a skydiver jumps from a plane. Of course, as he jumps from the plane, the force of gravity is going to pull him down, and air resistance is also going to be pushing back against his body. And as he falls faster and faster, the air resistance is going to build up, and that force is going to become greater and greater. And so the net force is going to be reduced because the gravitational force is staying the same, but now the air resistance force is getting more and more and more. So the net force is reduced and his acceleration slows. When the air resistance becomes as great as the force of gravity pulling him down, his weight, the net force is zero and his acceleration is going to terminate. It's going to end. So he's reached terminal velocity. He's not going to accelerate anymore. But again, he's still falling. He hasn't stopped falling. His acceleration has ceased, but not his fall. So he's going to continue to fall at a constant speed. And for the average skydiver, this is pretty fast. It's about 200 kilometers per hour or 120 miles per hour. So let's look at, remember the video we watched last week about the experiments of falling objects first with air resistance and then in a vacuum. So let's say we have a tube a little smaller than the vacuum chamber we saw last week, and we have a coin and a feather, and there's air present in the tube. So as we drop them from the same height, the feather has very little mass compared to its surface area. So it's not going to take a long time for the air resistance to build up enough force to equal the force of gravity pulling that light feather down. So it's going to reach its terminal velocity very quickly, and then it's going to continue falling at a relatively slow speed. The coin, however, has a lot more mass in relation to its surface area, so the air resistance doesn't build up as fast. As a matter of fact, in a short distance like this inside this tube, the coin is probably not going to reach its terminal velocity. So the coin is going to continue accelerating and hit the bottom of the tube much, much faster than the falling feather. But now let's take the air out of our tube with a vacuum pump and drop our coin and feather again. So now the coin and feather are falling just in free fall with no air resistance, what do you think is going to happen? Is the feather going to hit the bottom first? Is the coin still going to hit the bottom first? Or are they going to fall together side by side? And of course, the correct answer is they're going to fall together side by side. In a vacuum, there's no air resistance. So the only force acting on the coin and the feather is the force of gravity. And they're going to fall together and land at the same time, just like in our video that we watched last week.